Hello, everyone. I wanted to make you a quick video to help with the derivative graphs in section 3.5. So we mentioned this, well, we started working with derivative graphs in section 3.2, I believe it was, when we were doing um, the derivative function. When we first started talking about the derivative as a function, we did derivative graphs there. And it's not as simple a process as you might think to try to go from slopes of your original to y values on your derivative graph. Um, it can be a really tricky thing to make your brain do. And then here in section 3.5, when we're working with higher order derivatives and we're taking first and second and third and fourth and fifth derivatives, we're getting into graphs again. And I wanted to kind of go through these and give you a video because this is not as simple a process as it might sound. So let's do this first example here. We are given three graphs, right? A, B, and C here. And the given graphs represent an original function, that function's first derivative, and that function's second derivative. And we have to figure out which graph is which. So one of these is an original, one of these is a first derivative, and one of these is a second derivative. Okay, so in order to start doing this, we have to remember what the connection between an original function and a derivative function are. So um, if we are increasing on our original function, so anywhere that our original function is increasing from left to right, it has positive slope, which means because it has positive slope, the y values of my derivative are going to be positive. And that means my derivative graph is going to be above the x-axis there. And again, that's because slopes on the original are y values on the derivative graph. So in the same idea, if we are decreasing on our original function, that means that our slope is negative. And that means that our y values on our derivative graph will be negative, which means those y values will be below the x-axis. They will be negative y values. So wherever our original function is decreasing, its derivative has to be below the x-axis. And then finally, anywhere that our original has a maximum or minimum value, so anytime we do one of these guys or one of these guys, this point where we hit the max and min, that's the point where we have a flat tangent line, which means that the slope of the tangent line is 0, which means on our y value, on our derivative, will be 0, which means we have an x-intercept there, right? Like y equals 0 there. So any point where we have a max or a minimum on my original, we have an x-intercept on our derivative. And for me, this chart was super helpful for me. This was one of those things that I wrote on every single one of my calc tests when it was handed out. I made this chart because it really helps me kind of work through this. But again, I struggled with this when I went through calculus. Hopefully, you're not struggling with it. But if you are, this chart really helped me. Hopefully, it helps you as well. Okay, so we have to figure out the connections between these. So we're just going to start looking at a couple of these graphs and see if we can start making these connections to say that one is the derivative of the other, or if we can definitively say that one of them is not the derivative of the other. So let's start, how about with A and B? Let's just start looking at these two. Okay, so let's just start with A. A has I always kind of start with with this bottom one. That's kind of where I start with this. So the places where my original has a max or min, that's where my slopes are 0. So basically the slope at x equals 1 is 0, and the slope at x equals 3 is 0 on this first graph. And so let's look at B here. And I have a 0 here where this has a slope of 0. And I have a y value at 3 where this is 0. So that's looking really promising. B could be the derivative of A. Okay, so let's just double check this and make sure. How about between 1 and 3? Notice that from x equals 1 to x equals 3, this function is increasing. I have positive slopes there, which means that if B is the derivative of A, that means that the y values on B need to be above the x-axis. They need to be positive y values. But the y values on B are negative here. B cannot be the slope of A. It can't be the derivative of A because the place where A is increasing, this is negative. B is not the slope graph of A. Okay, so let's go back to the drawing board. Instead of starting with A and looking at B, let's go the other way. Let's start with B. Okay, so B has 0 slope at x equals 0, at x equals 2, and then somewhere over here beyond x equals 3. So let's come back to A and see. Oh, this where the slope is 0 here, A is 0. Okay. Here at x equals 2, I have a slope of 0 on B, and I have a y value of 0 on A. And also over here where I have a flat slope over here beyond 3, I also have a y value of 0 beyond 3 over here. This looks really promising. So again, let's double check. So how about between x equals 0 and x equals 2? Well, my B graph is decreasing. That means my slopes are negative there. And between 0 and 2, my y values are negative on A. That's great. That matches. And then look at beyond 2, from 2 x equals 2 to whatever x value this is, we are increasing, which means my slopes are positive, which means, oh, the y values here are positive as well. So this matches these guys. And so in here, you can kind of, so this definitely, I would say A is the derivative of B. Hopefully you see that, because where B has a flat tangent, A has a 0. Where B is decreasing, A is negative. Where B is increasing, A is positive. And if you want to get even more into the nitty gritty here, just to kind of solidify this home, notice that here these slopes are slightly negative. They get more steep, which means more negative, and then they start to flatten out and become less negative. The same thing happens here. You have a smaller negative, and then you get more negative, and then as your slopes flatten out again, these start to even get less negative. It matches. So A is definitely the derivative of B. Okay, great. So now that we know that A is the derivative of B, we still don't know if A is the original, or sorry, A is the derivative of B. I don't know if B is the original and A is the first derivative, or if B is the first derivative and A is the second derivative. So we have a little bit more work to do. So let's look pairwise at a couple more. I'm just going to do B and C. I'm just going to pick two of them and see what we've got. Okay, so B, again, I start with my 0, like wherever I'm flat. So B has a slope of 0 at 0, 2, and something beyond 3. Okay. And notice Y has a 0 at 0. It has a, oh, but it doesn't have a 0 at 2. I would need a 0 right at 2. But this doesn't have a 0 right at 2. So C is not the derivative of B, which is good because we already know that A is the derivative of B. And so let's look the other way. Let's start with C. C has a flat slope here and here. So I know that my slopes are 0 at x equals 1 and x equals 3. Oh, and my y values are 0 at 1 and 3 here. Great. So let's check the increasing and decreasing bit. C is increasing from left to right when we're less than 1 here. And notice my y values over here are positive. That matches. And then from x equals 1 to x equals 3, C is decreasing, which means my y values over here should be negative if this is the derivative, and they match. And then beyond 3, we start to increase again, which means we should have positive y values, and we do. So we can see here that B is the derivative of C. Okay, so that will tell us what we need to know about which is the original, which is the first derivative, and which is the second derivative. Now we just have to figure out what all this means. So which is our original, which is our first derivative, and which is our second derivative? Okay, so A is the derivative of B, and B is the derivative of C, which means C has to be my original so that B can be the derivative of it. And then A is my second derivative because it's the derivative of B. So now I know which one is my original, which one is my first derivative, and which is my second derivative. So this is kind of a slow, painstaking process, but I would just start pairwise with some of these graphs and compare the slopes on one to the y value of the other, and just trial and error, figure out which one is the derivative of which one. Go slow, take your time, and this is a really hard thing to make your brain do. So practice and practice and practice some more, and don't give up. It will come to you. It just takes some time to wrestle with until this kind of completely makes sense. Okay, and then the last one that I wanted to kind of mention is with number 5. This graph that I'm given represents acceleration. So this is an acceleration graph. That means this is like my second derivative graph if my original was position. Okay, so this is acceleration. When is the object slowing down? When is the object slowing down? So if in my object is slowing down, what would it mean for something to slow down? Well, to slow down, I need my velocity to be decreasing, right? We need our speed to be going down in order to be slowing down. Our velocity needs to be decreasing. Okay, well, velocity is the derivative of acceleration, right? This is acceleration. And velocity, which is our original graph, where this is my derivative graph, needs to be decreasing. So basically, v of t is like my original function, and acceleration, which is the one that I have, is my derivative. And I know that my velocity needs to be decreasing. So if I'm decreasing on my velocity graph, what do I need to be doing on my acceleration graph? Well, acceleration is the slope or the derivative of velocity. So if my velocity is decreasing, that means the derivative of that thing, which is the slopes, need to be negative, or sorry, the y values of my acceleration, which are the slopes of my velocity, need to be negative, which means we are below the x-axis. So
When is the object slowing down? What that means on this graph is it says, when is my velocity decreasing? Well, on our graph, that means where are the y values negative? Where are my y values below the x-axis? Well, from this graph, I can see that my y values, my velocity, my acceleration, the slope of my velocities is negative from x equals 0 to x equals 2. So we are slowing down. So when is the object slowing down? It's slowing down from time equals 0 to time equals 2. Or if you want to write that in interval notation, we are decreasing anywhere our time is between 0 and 2 inside this interval in interval notation. Okay, hopefully that helps you kind of work through some of these questions in section 3.5. Again, it's a little confusing with the graph stuff. Keep working at it and you will wrestle it into submission. Just don't give up and you can do this. Have a great weekend and I will see you next time.